Very well. So now unit vectors. Now that we define these objects, am I right? We said that, hey, we have these objects, these vectors, with different lengths, with different magnitudes, am I right? How do I construct a vector that is much more manageable and has a magnitude, it has a norm, it has a size, it has a length which fits everywhere? There we define unit vectors. Okay. When we're talking about unit vector, it means that the length of that vector is 1. So the definition of unit vector, wherever you see unit vector, it means that you are dealing with a vector with magnitude length 1. Why we are doing that? Think about the weather map. Suppose you're interested in knowing what's the weather map like from San Jose to San Francisco. Okay, are you going to just use a very long vector? Of course not. These vectors changing the direction at any coordinates. That's why we are interested in scaling these vectors and using the small vectors. Hurricane Sandy, as you can see here, you have a lot of small little arrows, these small little vectors representing the behavior. As you can see, we don't have a very long vector here. All of these vectors are scaled. They have smaller size or magnitude. One method, one way to scaling these vectors is to use unit vector. So if you think about these vectors with smaller sizes, smaller magnitudes, it shows the behavior of this hurricane, Katrina, for example, much more easier, much more better. Locally, you can see these behaviors much more easier. So one way, one method is to use unit vectors. So how do I scale a vector? This is the method that we use to scale a vector. So these are the terminologies that you need to know. Scaling a vector. Scale a vector. How to change the length of the vector to make it equal to 1. Okay, very good. So this is the way that we're going to do. This is the way that we're going to scale a vector. Let V be a vector, be any vector. What are you going to do? You're going to take vector V and divide vector V by its length. We take this vector and divide its components by its length, by its magnitude. Okay, so this is my vector V, divide by the length of vector V, and since it's a unit vector, I'm going to represent it by U. Usually we use U when we are referring to unit vector, the vector with the length 1. Okay, give us an example. Let vector V be equal to, let's see, the first component be, for example, 3, and the second component be 4. This is my vector V. What is the magnitude of this vector? The magnitude of this vector is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, or the square root of 25, which is 5. So if you graph this vector, use a ruler, you're going to see, if you measure it, the length, the size of the vector is 5. It's not a unit vector. Definitely. The definition of a unit vector says, hey, I have a unit vector if the magnitude is 1, but it's not. So V is not a unit vector. Is not a unit vector. So how do you make a unit vector? You're going to take vector V and divide it by its magnitude. V divided by the magnitude of V. What is V? V is defined as 3, 4 divided by the magnitude, which is 5. What do I mean by that? It means that I'm just multiplying the components of this vector by a fifth. Scalar multiplication. This is going to be 3 over 5, 4 over 5. So this is a scalar multiplication. So how do you show this new guy is a unit vector? We can show that U has size 1. So what's the magnitude of U? The magnitude of U is defined as the square root of 3 over 5 squared, 9 over 25, plus 16 over 25, which is equal to the square root of, they have the same denominator, 9 plus 16 over 25, or the square root of 25 over 25, or the square root of 1, which is nothing but 1. So this new vector is actually a unit vector. We can show that U has size 1. I just showed that U is a unit vector. So U is a unit